In this presentation, we'll introduce the fundamental idea of filtering, which will appear in many guises in this course. Filtering refers to the fact that for many dynamic systems, the system's output behaves differently depending upon the frequency of the input. A good example is music coming through the walls of an apartment. You'll hear the low-frequency signal, the bass, but you will not hear the high-frequency signal, the treble. So the wall, as a dynamic system, acting on an input and producing an output, is a filter, removing some frequency content and passing other frequency content. Let's consider a linear time invariant system with input X and output Y. We'll consider how it responds to two different inputs, a higher frequency input X1 and a lower frequency input X2. In response to the higher frequency input X1, the output Y1 is nearly of the same size. We say that signals at this frequency are passed by the system. When the lower frequency input X2 is applied, the output does not respond nearly as much. Y2 is small in comparison to Y1. We say at this frequency that input signals are rejected. This is the fundamental notion of filtering. Some frequencies are passed through and other frequencies are rejected. Which signals are passed and which are rejected depend upon the dynamics of the system and are related to the system's characteristic values. In this course, we'll spend a considerable amount of time trying to understand filtering and trying to understand the properties of differential equations and how they result in filtering. We'll cover this material in great detail when we get to frequency response near the end of the course. For now, we simply need to introduce the concept and to understand a few basic notions. Let's now examine filtering by looking at an actual mechanical engineering application. Let's examine the suspension of an automobile. The suspension serves two purposes. The first is to maintain a distance between the car's body and the ground, so that as the car moves across the road, parts of the body do not come into contact with the ground. For this purpose, the car's body must follow the contours of the road. The second purpose of the suspension is to protect the occupants from vibration caused by an uneven road surface. For this purpose, we need to have the unevenness of the road not transmitted through to the passenger cabin. Therefore, a suspension should act like a filter. It should pass some frequencies and reject others. Here is a car mounted on a shaker system. As you look carefully, you'll note that the low-frequency motion of the shaker is passed through to the car's body, but the high-frequency motion of the shaker is not passed through. This is the proper role of the suspension. It is to pass the low-frequency motion, which corresponds to the contours of the road, and to reject the high-frequency motion, which corresponds to the roughness of the road. Thus the car suspension acts as a filter, passing one set of frequencies and rejecting another. We'll now look at the response of a linear system which has an impulse response that is a pulse, as shown here. We'll look how it responds to inputs of different frequencies, and we'll consider three cases. The first is low frequency, which is X1. The second is omega equals 2 pi over cap t, where cap t is the duration of the pulse in the impulse response. And the third frequency we'll consider, x3, is a high frequency signal. It can be shown that at low frequencies, this system passes through the input signal, and thus the output in response to x1 will look much like x1. In response to signal x2, at a frequency of 2 pi over capital T, we find the output is 0. So this signal is completely rejected. In response to the high frequency signal, x3, the output will be very small, so this will be rejected as well. One can show that if the input is at a frequency greater than 1 over t in hertz, then the output will be largely rejected, and if the input is below this frequency, it will largely be passed. This frequency is called the cutoff frequency. It's also referred to as the bandwidth of the system. The frequencies between zero frequency and the cutoff frequency are referred to as the passband of the system. We'll now look at a special form of plot to indicate this behavior. It shows the ratio of the output amplitude to the input amplitude as a function of the frequency. If the output is of the same size as the input, then this ratio will be 1. This plot shows that below the cutoff frequency, the output amplitude is almost the same as the input amplitude, and above the cutoff frequency, it is greatly reduced. For this particular filter, there is no output at the cutoff frequency, as we discussed before. For other filters, there may be an output at this frequency. This sort of system, which passes through low frequency and rejects high frequency, is referred to as a low-pass filter. The automobile suspension that we discussed earlier is also a low-pass filter. So we've discussed some low-pass filters. The obvious question is high-pass filtering possible? Yes, it is, and it's not only possible, it's actually quite useful. Suppose you have the problem of collecting some data from an experiment. The data is collected from a sensor, and the sensor output is drifting, perhaps in response to the temperature. You're interested in the high-frequency content of the signal, not the low-frequency drift caused by the changes in temperature. How do you get rid of the low-frequency content and keep the interesting high-frequency content? How do you remove the drift? For this purpose, you need a high-pass filter. What you'd like to do is take all the data you collected, your signal, and pass it through a high-pass filter. The high-pass filter will remove the low-frequency content, the drift, and leave the high-frequency content, the signal that you want to keep, that you want to analyze. So you want a filter that has a response versus frequency that looks like this. Again, we plot the ratio of the output amplitude to the input amplitude as a function of frequency. We show that the low frequency content is being rejected and the high frequency content is being passed. Such a high-pass filter can actually be developed from a low-pass filter. The diagram at the bottom of the page shows how to accomplish this. This sort of diagram is known as a block diagram. We'll be using these quite a bit later in this course. This diagram is saying the following. Our input is x of t. X of t travels along two paths. On the lower path, it goes through a low-pass filter to produce x sub 0. X sub 0 is the low-frequency content of x of t. This low-frequency content then is subtracted from x of t. That's indicated by the circle with the plus and minus signs added. The subtraction of x0 of t from x of t produces the output y of t. So y of t is x of t minus x0 of t. X of t is the original signal, and x0 is the low frequency content of x of t. Thus, we're taking away the low frequency content from x of t, leaving the high frequency content. This block diagram is sure to be confusing, since we haven't covered block diagrams as of yet in this course. So let me explain it again in a few words. The low-pass filter removes the high-frequency stuff from the signal and produces x0 of t. This signal is then subtracted from x of t. When we subtract the low-frequency material from x of t, we're left with just the high-frequency stuff. Now this idea will work with any low-pass filter. From any low-pass filter, we can develop a high-pass filter in this fashion. Let's suppose we use the low-pass filter that we studied earlier in this lecture. That is, a pulse of width cap t and height 1 over t. We'll refer to the impulse response of this low-pass filter as h sub l. Now, we know that the low-pass filtered signal, x0, is going to be the convolution of h sub l with its input, x of t. And since y of t is x of t minus x0 of t, we can now do a bit of algebra. We'll recall that if we take a Dirac delta and convolve it with a signal, we get the same signal. So x of t is the Dirac delta convolved with x of t. That allows us to group terms here in the bottom part of the equation. We find y of t is the quantity delta of t minus hl of t convolved with x of t. So delta of t minus hl of t is a high-pass filter's impulse response. We'll denote the impulse response of the high-pass filter as h sub h. And so h sub h is delta of t minus h sub l. The output y of t then is h sub h convolved with the input x of t. And this acts to be a high-pass filter, removing the low-frequency content from x of t. So what does this impulse response look like? H sub h is delta of t minus hl of t. And hl of t was a pulse that was t wide and 1 over t high. So when we subtract that from delta of t, we find the following graph for h sub h, the impulse response of the high-pass filter. It has a Dirac delta at time 0. Then it is negative 1 over cap t from 0 until cap t, and it's 0 otherwise. Now, it should be noted there are many kinds of high-pass filters, and this particular one that we derived from the pulse low-pass filter is just one example.